Welcome to this talk on mining for bugs with graph database queries. Just for my information, I've given a talk like this before at last year's CCC. Who's seen the talk with the same title? Nobody? Great. So I could have just taken the slides I already had. But okay, I made some new ones as well, so well, hopefully it's even better. Okay, so this talk is about vulnerability discovery, and if you have nothing to do with vulnerability discovery, just to give you a short working definition, vulnerability discovery is the art of navigating inside piles of junk. The goal is to uncover small programs that we can use to our advantage. So I think this is so I was searching for a picture for a very long time, which kind of, gives you, communicates the feeling that you have when you first see a new code base and somebody tells you, please find something exploitable in here. I think this picture, fits it pretty well. Now, the idea of my work is to apply pattern recognition for vulnerability discovery. And in contrast to many approaches that you see, particularly in academic work, I don't try to focus on exact methods where you reason about like confined regions of code in great detail, and you assume that you can exactly model all of the instructions of the language that you're looking at. But instead, I'm taking a pattern recognition perspective where I try to recognize as opposed to detect bugs. So this is mostly inspired by the books you see there below, which is more from the engineering field, where you're kind of aware of the fact that all of the stuff that you're dealing with is very imperfect. So you're looking at it in terms of a signal and noise. And the question is whether we can use these methods and kind of apply them to what traditionally people have been doing with very exact methods, kind of represented by the books that you see on the top. Now, an important theme to this is that I'm not trying to build something that automatically detects bugs, but instead, these are supposed to be tools that help auditors in day-to-day work. So, in a way, they enable people to automate what can be automated, but also make use of their ideas and their knowledge of the code base to spot vulnerabilities. Now, I've been doing this for quite a while now, and recently I noticed it's been 3.5 years. Fortunately, I finally finished my thesis on this, and this is going to be coming out very soon, so in November 15. So if this stuff seems interesting to you, please take a look. So, a thesis is a document that's, you write it for very long, but then nobody actually takes a look at it. So if you ever want to hide any secrets somewhere, you best do it in a thesis. But hopefully, maybe one person or two in the room finds this interesting and actually checks this out. That would be very, very cool. Okay, so we're going to be looking at 2 chapters, essentially, in this. One of them, that's like the basis of all of this work. It's a graph mining platform for vulnerability discovery. Built on that graph mining platform, I explore the 3 main directions of machine learning, of unsupervised machine learning, and see whether those directions, whether those methods can be used to help us find bugs. And I can't tell you about all of these in the talk, but I'm going to talk about one of them, which is how clustering can be used to help you identify vulnerabilities. And the nice part here is that actually this method will again generate queries for the graph database system. So you actually see exactly what the system has learned. So this is something that is very often criticized about machine learning, that you can easily create a program that kind of classifies something, but you don't really know what it does. So in the security context, that's not really good. But if it actually outputs a query in the end, then you can see what it has learned. And if it's rubbish, then you will also see this. All right. So let's get to the first part. This is about the graph mining platform, and this combines 2 well, two things which seem to have not so much to do with one another when you start off. On the one hand, we have a good old computer science compiler construction. So what compilers do to optimize your code, analyze your code, remove dead code, stuff like that. And on the other hand, you have the shiny new graph databases. And the question is, how can we combine these to actually get a good system for assisted vulnerability discovery? And I want to start off with an example. This is an example of a bug found by famous German hacker Stefan Esser. It's a bug that he showed in his Syscan 13 talk. And well, he showed a lot of really cool bugs in that talk, and this was more of a side finding, you could say. But it's interesting because of the way he found it. And it's also interesting because it looks very much like a lot of other bugs that you will see all over the place. So let's quickly go over this. There is a variable called namelen, and it's a 32-bit integer. And apparently, it comes from a network because we're using a function called N2HU. So we're converting it from network byte order to host byte order. So this looks a lot like this might be from the network. And what then happens is we allocate a buffer, and we add 1 before allocation. And clearly, if we control this namelen field completely, then if we use a maximum integer, then what will happen is we get an overflow. And actually, it allocates 0 bytes. And then it copies namelen bytes into the buffer, so you get a heap-based buffer overflow. So this is a very classic thing. You see this all over the place. And now the question is, how did he find this bug? And particularly when you talk to academics, they will expect something really evolved right now. So did he use a white box fuzzer enhanced with symbolic execution, or some machine learning powered anomaly detector, or theorem proving or model checking? But it turns out all he did was he used grep, right? So this is the regular expression that he used to uncover the bug. And you can see he's kind of looking for allocations. And inside those allocations, yeah, there's supposed to be a summation or any sort of arithmetic operation. And what he's encoding here is the fact that if people do arithmetic inside the allocation, then that's often a source for heap-based buffer overflows triggered by integer overflows, because obviously there's no sort of check after the summation or whatever it is. So there are going to be a lot of cases where this is not problematic. Maybe a check was done before or so. But these are good points to start. And yeah, I think we can learn a lot from this. So first of all, even if you take something as primitive as grep, this can be a very powerful tool if you allow an analyst to actually guide the analysis. If you allow them to introduce some knowledge they have of how things break in this particular language, in this particular programming environment. Another interesting part is when you think of this grep query, it encodes domain knowledge. So you can think of it as a model of a bug. And then finally, high false positive rates are not that bad. It's not like intrusion detection, where 1% false positives is, well, you can't really use a system with 1% false positives because it means the administrator is going to be knocked out of the bed like every few minutes or so. Here, if you have like 100 hits or so, and I don't know, 10 of them are interesting, so be it. I mean, that's pretty good. If 10 of them are actually vulnerabilities, wow, that's not a problem. Okay, so here's the goal of what we want to build. We want to build a robust search engine for source code. So there's going to be a robust parser. I'm not talking about what robustness means in this talk, but yeah, there are a couple of other talks around on this topic that I've already done, and I talk about this in great detail, but I figured out nobody really cares, so it's a parser. And you use this parser to import the source code into this graph database. And in the back, you have these pattern recognition algorithms that can be used. But most of all, the analyst can query this system, get responses, adapt the queries, and query again. That's the idea. All right. So the first question we need to ask ourselves is, what do we actually need to be able to model inside a query? So what are the things that the auditor might want to specify? And I think the three things, so after analyzing lots of bugs, we found that the three things that you want to specify is what do the statements look like? Can we get from one statement to another? And how do the statements affect each other? And the nice thing is we don't have to come up with new ways of dealing with this because compilers need to deal with this all the time. So let's see how compilers deal with this. So in compiler construction, you have all sorts of graph representations of code. So for example, there's the abstract syntax tree. This tree essentially shows you exactly how language constructs have been nested to create your program. So you can see, for example, okay, there's an if here, and there's a predicate of this if, and the predicate is x is smaller than max. And then there's a statement nested inside the if, and so on. Now, another thing that you probably all know is the control flow graph. This is what you get in IDA Pro, for example. This tells you how statements can be reached, as in what conditions need to be true for me to reach a statement. So for example, here you see that x needs to be smaller to max to reach this statement y equals 2 times x. And then here's one that not so many people know. It's called the program dependence graph. And the program dependence graph gives you data flow information. So you can see, for example, that there's a value called x, and it's produced at one statement here, and then it's being used by another statement here. Okay. So these are the three main data structures that can be used to analyze code with compilers. And the problem is, you can't just choose one and do everything with this. So none of these is perfect. If you take a look at a typical query, it's more like, find me a call to foo in a statement where data flow exists to a statement that contains a call to bar. So actually, what you're doing is, first you're describing syntax. You're saying, find a call to foo. That's something syntactical. Then you're saying, but now I want to reason about data flow. Now I want to see where this data is propagated to. And then again, when you follow the data flow link, you want to go back into the syntax because you want to find calls to bar. So there's this need to create transitions from the syntax tree to the dependence graph and back to the syntax tree. And the question is, can we get a representation that has it all? And the main observation to do this is that actually in each of these graph representations, there's a node for each statement, right? So why not just merge them, right? I mean, the main trick here is that we actually have labels on the edges to distinguish the different types of edges that we have. But now we have a data structure that represents all of this in one. And this is what we call the code property graph. And now the question is, can we maybe describe vulnerabilities as subgraphs in this code property graph? Now, once we have this, we wanted to somehow store it, to query it. And we try to store it in relational database management systems because there are a lot of good reversing tools that use relational database management systems. So we're thinking, why not? And we failed completely, writing a lot of code to just map graphs to tables, and failed. Then we tried out document databases for some reason. I'm not sure why, but of course that fails as well because mapping documents to graphs is hard. But actually, mapping graphs to graphs succeeds immediately, so yeah, we turned out using a graph database. And just a short note about the relational database management systems. Of course, you could just create tables for nodes and then create like a join table for the edges, but this doesn't scale. So the lookup time that you get on the join tables will become proportional to the size of the graph, and this will become very inefficient. So this is like one of the main things that graph databases give you natively. the support for these, for efficiently querying these graph structures. Okay, so graph databases, they don't use tables as their native storage format, but instead they use what is called a property graph. And a property graph is really just a graph where you can attach like dictionaries to the nodes, like Python dictionaries or hashes if you like, and you can put labels on the edges. That's it. Right? So here's an example. So here you have a name and an age attached to each of the nodes, and you have different kinds of edges, so created and knows. And with this graph at hand, the nice thing about the graph database is you already have languages to query this. And there are two very popular languages. Well, actually, there are a lot more, but you know, Neo4j, the most popular graph database, gives you two. One of them is the Cypher query language, which is not so well suited for what we want to do. And the other is Gremlin. And Gremlin is pretty basic. You choose a set of start nodes. Then you describe how you want to walk the graph. And if it's possible to walk the graph according to your description, the nodes that you reach, they will be returned. That's it. So for example, return all objects created by people over the age of 30. That would be the start node, so all the people with age bigger than 30, and then follow outgoing created edges. Right? So this is what that would look like in Gremlin. So Peter and Josh are both over 30, right? And now we start at those, and we then follow all the created links, and we stop at the things that they've created, and this will be returned. That's it. Now the really nice thing is that you can get something like stored procedures here. Once you've defined, you know, something that you commonly look for, you can give it a name. So you can say all the people who are over 30 who've created something nice for us are people we can fire now, and then you can just say people we can fire now, and you know, yeah, you don't have to rewrite this thing over and over again. And you can create really complex traversals, they're called, and you know, save them in these pipes and then reuse these pipes all over. So initially this stuff was created mainly for social networks, right? So graph databases, I think one of the events where they became publicly more known was when Facebook introduced their graph search, and they allowed you to look for all sorts of fun social things. So for example, you could look for people who like English Defense League and curry, or you could look for mothers of Catholics from Italy who like Durex, right? And those were the kind of examples that, you know, got a broader attention. Well, the nice thing is you don't have to store useless crap in databases, graph databases. You can also store, for example, the code property graph in a graph database, because by definition, of course, that's how it was supposed to be built, it is a property graph. Okay? And then once you do that, you can use this stored procedure trick to actually build a domain-specific query language for vulnerability discovery, where you encode all of your ideas of what kind of things you would like to check for. And we did this, and we built a platform, and you can use this, download it. It's, well, yeah, everything's available. The platform is called Yearn, and it processes C and, you know, parts of C++. And there's a Python scripting interface and some shell utilities you can use. And it's actually been tested to work on other people's machines, so it's made me very happy that it doesn't just run on my machine. This is probably the first of my projects where this is true. You can download it at mlsec.org/yearn. Right. So let's take a look at what this system does and how you can use it. So the first step is you import your code, and the code is written to disk. And the graph database server can then be started, and it accesses the disk. And this graph database server exposes a REST API. So you can see this comes from web people. And I tried to hide this a little bit because, you know, I don't really think the whole web stuff is necessary at this point. So I wrote a little library for you. It's called Python Yearn. And you can just use this database without knowing that there's this REST stuff in between. right? So very comfortable. Now you can, just import the Yearn library, you specify a query, you connect to the database, you run it, you print the results, right? That's it. That's a fully functional script here, except for the fact that I did not include a query. Or if you like the shell, you can use the shell utilities. Right? So we did a practical evaluation of what this tool can do. I'm just going to make this very short. In the original talk, we talked about all of the details of this, but that was actually not so interesting. The point here is this is not some purely academic thing that really doesn't produce results, but in fact we used the Linux kernel as a case study, and I actually got somebody in the industry to use this. So this is my good friend Nico Golde here from Qualcomm, and well, he said that they found about 100 issues in an internal audit. Now I don't know what they qualify as issues, and we were not able to he was not able to really give this out. But then we also did some open queries that we could share with everyone. So we did 2 queries for buffer overflows in the Linux kernel, 1 for 0-byte allocations, 1 for memory mapping bugs, and 1 for memory disclosure bugs. And this was the outcome. We found 18 vulnerabilities acknowledged and fixed by the developers, and you can see we also got CVE identifiers. So these are not just some problems that security people like to think of as problems, but also the developers said, okay, yeah, this is a vulnerability. Let's give out a CVE. All right. But now for a case study, and I think this is the more interesting case study, VLC. So here's what you see. Here's what you would do if you were to run this on VLC. So first you run Yearn to import VLC, and this takes a while, and then you start the Neo4j graph database server, so that's the graph database, and you can point your browser to this address here just for some statistics. So you can see that the VLC code produced 2 million nodes about, and 5 million properties, 4 million or almost 5 million relationships. These are the edges in there. Yeah, and it takes about 705 megabytes. Now in those 705 megabytes, not sure if in those, but yeah, it should be in those. There's also an integrated text search engine based on Apache Lucene, and we're going to use that for start node selection. So this is like an extra feature that Neo4j gives you. So here's an example of a very simple Yearn query. So this is just Lucene really. So let's say we want to have all the files that have the name dmux inside them. So we can write this query, type as file, and file path is dmux, and we can pipe this to Yearn lookup, and it will give us all of these paths and also the IDs for this. Now you're probably thinking, okay, so why do I need this? I could just use find, right? So now comes the magic. The magic is that once you are at these file nodes, you can actually descend into the contents of these files, right? So the entire code base is just one huge graph, and you can transition from the different representations. You can transition from files to their content, you can transition from syntax trees to their control flow graphs, and so on. You can also transition from functions to the functions that they call. You have a call graph. All of this is possible. So we put this type as file and file path dmux into one of these custom steps that we defined, which is called query node index, which would just execute this Lucene query. And from there on, we follow outgoing edges and take only those which are labeled as functions. So suddenly, you have all the functions inside files called dmux, right? Okay. So let's take this for a spin to find vulnerabilities, and let's take a look at the SSH bug again, lib SSH bug again that we saw, that Stefan Esser found. So we might want to formulate the following query in our head before we, make code out of it. So let's get calls to malloc where the first argument contains an additive expression and a call to MemCopy is reached by data flow, where the third argument also contains an additive expression, and the two additive expressions are not equal. Right? So you can formulate something like this. it's, let's see, yeah, what's the idea? The idea is that the size that's being calculated is unequal to that of the buffer that's being reached, and it's pretty unsafe because you're doing the additions directly inside the allocation then in the copy call. Now here's what that would look like as a query. Get calls to malloc, that's one of those utilities, and from there go to the its first argument, which is the amount to allocate, and store that, right? Now take only those which are additive expressions, and from those additive expressions, so you're in the tree now, you go up to the enclosing statement, and now you can follow the data flow links. So now you can say, follow all data flow links where we, and now you go back into the AST, find calls to MemCopy where the third argument is unequal to the stuff we saved. That's the first argument to malloc. And this is also an additive expression. That's it. You type that, you pipe it into your lookup, you sort it, unique, you use your location to get the actual locations, you pipe it to foo, right? Foo's your file now, you cat foo, and you get 4 hits in the entire code base. And I immediately thought, oh, MP4 looks nice. I have some MP4s. All right. So grep foo for MP4 and your code, which will output the code. And this is what it outputs. And I would ask you how to trigger this bug, but it already says it. So what you see here is code to parse MP4 files. And here's your malloc, and it has an additive expression inside. So let's insert 7. Then we would allocate 7 plus 1 minus 8 is 0. Okay. And then here's the MemCopy that's actually being reached by data flow. And the third argument here also contains an additive expression. And this time it is size minus 8. And if we insert 7, then that's actually minus 1. So we have a buffer that's allocated to close to 0 byte. We copy minus 1 cast to unsigned integer, which is max int, into it, and there we have our buffer overflow in VLC. All right. So that's the first example. Of course, the question kind of arises, what do I search for? Well, one of the things that I found very inspiring about this question is something said in a book called The Art of Software Security Assessment, which is a really cool book if you're into code analysis. And in that book it says, in fact, 2 of our authors typically start reviewing a new code base by finding the equivalent of the util directory and reading the framework and glue code line by line. Now, what does it mean? That means let's understand the language first that is being spoken here. And by that, I don't just mean the programming language, but the abstractions that are being used. And if we can find something that's fundamentally hard to use about these abstractions, then, you know, looking for problems related to these is probably going to pay. So in VLC, I took a look at the stream processing API, and that's mainly located in VLC stream.h. And there's one interesting function that you can find here, which is the function called stream size, and as the name implies, it returns the size of the stream. Now, clearly, a stream, you know, this could be some media file, and you would want your videos to be larger than 4 gigabytes, so you'd have to return an int64 and not just an int 32. So you want 64 byte. Now, the problem, of course, is if you have a 32-bit platform, then all of the allocations that you're going to be doing with these, well, you're going to have to be very, very careful about these because they're probably going to overflow or be truncated. Yeah, so the idea was, oh, and this is realistic for an attack because, you know, a video can be larger than 4 gigabytes and nobody would say, oh, wow, this must be malicious. No, it's just a video. That's why it's that big. All right, so let's look for truncations inside allocations related to this. So give me statements containing calls to stream size and the symbol int64. where data flow exists to statements containing the symbol malloc. And this query is much smaller, right? There's get cost to again, so get cost to stream size, go to the enclosing statement. From there, take only those that contain int64, and now follow data flow and see what we can actually reach, and filter out only those where malloc appears. So these are allocations connected to the stream size call. And this is what you get. Not very much. They're not too interesting, except for this one, because this one is in the automatic updater. So here's the code for this. What you see is here, stream size is being called, right? And there's this integer called iRead, int64, and it's being used inside the malloc here. And again, we add 1. Now what happens is, on a 32-bit platform, the argument that's expected by malloc is actually 32-bit in size. So it first takes this iRead, it actually adds 1, and that's not problematic yet, so you still have a 64-bit integer. But then when it's passed to malloc, at that point, it needs to be truncated. So again, if you choose this to be the maximum size of a 32-bit integer, then you add 1, what you actually get is 0. And then down here you have a stream read operation. Stream read is pretty much like MemCopy, but much better, as you'll see in a minute. And it again reads iRead bytes into this buffer, which is maxed in. So there you go, you have your overflow again in the updater. Now you're probably going to say, okay, the updater, there's probably going to be some sort of, signatures involved to verify if the update is valid or not. The nice thing is all of this actually happens before signature validation, okay? And also using HTTP, so it's just clear text that you need to transmit here. All right, so executed before verification, just said that. So I tracked this out. I edited EDC hosts to point update videolan.org to my personal little web server, and I created a file with max int size containing all A's. I attached the debugger to VLC, I checked for updates, and here's what happens. And that's very, very convenient, because typically, when you start to debug something like this, you have to do a lot of work to get the instruction pointer to point to your A's, right? But in this case, actually it worked immediately, and we're going to see in a minute why that is the case. The nice thing is, arguing in favor of patching, gets very, very easy if you already control EIP. There's no question now. This is a security bug. People can tell my program where to jump next. Okay. So notes on exploitation and why this worked. So for one thing, and this is important, you don't actually have to transmit a 4 GB file. That would just take too long, and that would not be cool. So instead, it's perfectly fine to use the content length field here and set it to that value. So you're actually telling it, eventually you will receive 4 GB. And now I'm just going to give you a few bytes for now. So the attacker also fully controls the amount of data to actually copy, because you can chunk the HTTP responses that you give. And this is the important part, stream read, so this version of MemCopy, actually copies in blocks. And in between these copy operations, it dereferences a function pointer. Okay. Meaning that if you can overwrite this function pointer, or if you accidentally overwrite that function pointer, as I obviously did at that point, then as it dereferences the function pointer, you already control where it jumps next. ASLR and DEP is typically enabled, but there's some position-dependent code that allows you to build a smaller up chain. The downside, this is multi-threading, so it's not so easy to exploit. All right, I have a demo exploit. I'm a bit running out of time. I'm going to do it anyway, I guess. So there you go. There's my VLC. It's a bit unstable, so it works every 5th time or so, but you fire it at 5,000 hosts, you get 1,000 shells, so what the hell. Check for updates, and it doesn't work. And it's, maybe this was not such a good idea. Oh yeah, wait, sorry. All right. Check for updates. Did I mess it up? Just a second. No, I didn't mess it up. Okay, something is broken. This is the thing with live demos. Don't do live demos. Okay, something is very broken. I think it lost its connection actually to the host. That's because this guy is supposed to send it data and then it actually displays something. But okay. Anyway, I'm running out of time. You can see the working exploit if you really want to see it in the CCC video. It does work, I promise. I'm sorry. Okay, so part 2. Vulnerability discovery using clustering. So once you explore lots of bugs with this, you start to see that it would be very nice to actually design some templates that you could fill out to find your bugs. So for example, if you take Heartbleed, then Heartbleed actually has the same structure as the bugs we looked at as well. So you kind of have this, this attacker-controlled payload field here. And again, there's this network to host byte order conversion. And in the original code, this check here was not in place. And then it eventually reaches the third argument of MemCopy. And since the check is not in place, you can copy more than you should. And by that time, you think, OK, let's just create a template for this. You know, get calls to some sync function. And then you want to describe what the arguments to the function look like, each of them, and how they should be checked. And if that's not the case, you know, output it. And so these are the kind of queries that I use these days. So not those long queries, but something like this. And this gives you grep-like functionality. But wouldn't it be much nicer if the system could also actually tell us what is inside the code base? So could it maybe tell us, these are common data flows. Can we get LS-like functionality? Can it automatically fill out this template for us to show us the most common data flows in the code base and the programming rules attached to this? So things like, there is always a check here. A related question is, if we have a bug already, can we maybe generate like a robust signature for this bug? So yeah, that's the scenario. Here's our template. We want to learn regular expressions for this, both for the sources and for the sanitizers of this. Yeah, and you can think of this as a little car. And there's what you're learning here is the model parameters. That's the driver of the car. And once you have that car, you put it into the code property graph. It drives down the code property graph. And you know, as a side effect, it gives you a list of findings. Now, conceptually seen, this is a machine learning problem. Yeah. Machine learning problem. What does machine learning mean? Well, it really just means you take data, you put data into your system, and it creates this model for you, so this driver. And then it uses that model to instantiate a predictor. And the predictor is a poor thing. It gets more of this data, and it needs to somehow make sense of this data. Right? Now, learning queries is the same. You have the source code, you put it into your little oven, and it outputs those template parameters. And then the query that you get, that's the predictor. And you throw more source code at it, and it drives down the code property graph and says vulnerable, okay, vulnerable, okay. That's the idea. Conceptually, we can borrow from signature generation here. So in signature generation, you take the data, and you first extract objects from it. You map this to a vector space, and in there you can use classical clustering algorithms to find similar objects. And then for each group of similar objects, you generate one of these queries. That's the idea. Now, I'm not going to bore you with the details. We built this oven, and if you're into this kind of stuff, you can read this up. Essentially, the objects we classify are invocations, as in calls to the functions. We then use a representation where each dimension of the vector space is actually associated with a regular expression. So that's a nice trick if you like machine learning. And we then use those regular expressions to instantiate the template. And if you're interested in the details, as I said, the thesis is coming out, but also there's a paper available already, which is called Automatic Inference of Search Patterns for Chain-Style Vulnerabilities. And just to quickly get to the results, this is the query that was automatically generated for Heartbleed, for the Heartbleed bug. So you can see it says that the third argument, there's a common flow in the database, which is the third argument is initialized by N2S. For the second argument, it found, okay, I don't really know how this is initialized, but it's always checked against null, telling the programmer this is a pointer. And then for the third argument, I find that there's typically some sort of comparison with a number. This is what's automatically extracted, and it looks pretty close to what we wrote manually. And the nice thing is if you run this, it doesn't just find the one instance of the Heartbleed bug, but also the other, right? So there are two instances of this bug. And these are false positives. So yeah, the system has false positives, definitely. Then we also use this on VLC and just ask, give us all the systems for MemCopy. And two of these were interesting in their own right, because by immediately looking at these, you already see, okay, this is dangerous. So here you have a buffer on the stack controlled by a variable called len. And there's some sort of addition in here. So this is essentially something like a locker. You can't do this in a safe way. If this is too large, then actually you'll have memory that's not allocated that you're actually copying to. And this found bugs. And then the other one is you have a get, some sort of get that controls the third argument to MemCopy. This found bugs as well. I'm wrapping up. These are the CVEs we got for these. This was pretty much just going over the 60 systems and picking these two, and these immediately output these bugs. All right, conclusion. I introduced the system to mine code bases for vulnerabilities, and it builds a bridge between program analysis and graph databases. And you saw that you can't just specify these traversals, these search patterns by yourself, but also you can get the system to enumerate what's there using learning techniques. And this is something that, on the one hand, tells you what you could look for. On the other, it gives you robust signatures for known bugs that you have. We found real bugs using this, so it kind of works. That's all I can say. Okay, thank you.